we are going to continue on our lecture on nuclear chemistry, which we started in the last class, and our presenter is going to be Latif. Last week, what we were able to do was explaining the different types of radiation, where we mentioned alpha particles, beta particles, the gamma particles, and we state their properties and reactions, nuclear reactions, which each of them occur. We also examine half-life of an element, where we said it is the time it requires the half of the element to degrade away. So today we are going to further what we have known about the topic, because it is very important we know how to differentiate between what we have learned in nuclear reaction and the common chemical reaction we used to encounter every day. And again, the radioactivity we have been emphasizing, we need to carefully consider what led to it. Do they just occur? Is it influenced? Or what are the factors that can make it occur? Then some applications, apart from the few applications we have mentioned the other time, where we mentioned nuclear bomb and nuclear power. We mentioned application in medical physics or medical science, application in environmental science, in food science, and in biochemistry. Today we'll be able to explain another form of application, although it also falls on nuclear power generation and nuclear bomb production. Then through various examples that we will learn today, we'll be able to know how to balance nuclear reactions. So let us start with the comparison between nuclear reaction and chemical reaction. Like chemical reactions we have been seeing, and which we are going to be seeing the rest of the course. We have learned the structure of atom and the periodic table, and I can remember one of the things we mentioned was that the properties of elements is determined by the number of electrons in the outermost shell, which in turn dictate the group at which the element belongs to, and that one now tells us, indicate how they will react. So invariably, chemical reaction take place by electrons in the outermost shell, because the electrons are the particles that react for chemical reaction to take place, unlike in nuclear reactions, where the reaction itself actually takes place in the nucleus. We have talked about that last week. The chemical reaction is as a result of the particles in the atomic nucleus. So that is the first difference. The second difference is we know the chemical reaction involves electron, and there are various ways at which electrons are chemical reaction take place with use of electrons. It can be by transfer, it can be by loss, gain, or sharing. But in nuclear reaction, since it is taking place in the nucleus, the issue of outermost electron does not arise. So the decomposition of the nucleus is what is responsible for nuclear reaction, where transfer, loss, gain, or sharing of electrons are the factors that affect chemical reactions. In a nuclear reaction, the protons and neutrons react inside the nucleus, and in chemical reactions it is outside. So this comparison is telling us the location or the site of the reaction that is taking place. In the nuclear reaction, it is inside the nucleus. In the chemical reaction, it is outside. Then in terms of energy, thank God, last time we talked about the enormous amount of energy that are generated, such that nuclear reaction can be used to provide power. So in that case, if we are considering and comparing the energy differences between chemical reactions and nuclear reaction, the energy difference in chemical reaction is assumed negligible. In fact, the energy is very, very small. Like the energy that used to take place in chemical reaction is around 1000 joules, 1500 joules, sometimes it's 42,000 joules, depends on reaction. But in nuclear reaction, we talk about hundreds of thousands of joules, millions of joules of energy that will take place. So in short, comparing energy of chemical reaction and nuclear reaction, chemical reactions have far greater energy in relation to chemical reaction. In chemical reaction also, isotopes, don't forget isotope that we said they are energy, they are atoms of the same element with the same atomic number but different number of neutrons or different mass number, the case may be. So those isotopes in chemical reaction, they react the same way because it is the electron that are reacting. So the neutron that are different, that one is not concerned for chemical reaction, since it is the electron that is reacting. But in nuclear reaction, the neutron, the reaction takes place inside the nucleus. That is what makes isotope different. So we expect that the reaction will not be the same. If let's assume we have an atom A with mass number 200 and the same atom with mass number 202. So if each of them will emit alpha particle, definitely the product that will be formed will not be the same. That is what we mean by this statement. In nuclear reaction, there's complete transmutation, change in transmogrification of element into other element. But in chemical reaction, it is just a combination or rearrangement, as the case may be, or substitution. There's no change in chemicals. If sodium hydroxide reacts with hydrochloric acid, what we are going to get is sodium chloride and water. Sodium will not change, chlorine will not change, hydrogen will not change, oxygen will not change. It is not that sodium will become calcium, but in nuclear reaction there must be complete transmogrification. And again, in nuclear reaction, we said there must be complete change in atoms from reactant to product. definitely there must be a detectable mass changes in nuclear reaction. But in chemical reaction, the equation must balance. The amount of product must be equal to the amount of reactant. If 40 grams of the total mass of reactant is 40 grams, we expect the total mass of the product to be equal to 40 grams. So those are the differences that we need to consider between nuclear reactions and chemical reactions. So let us now look at the mode of radioactivity, the mode of emission of particles. What causes it, or do they just occur, or something influence it? So let us look at natural radioactivity. Spontaneity is the key word in this place. Spontaneous. Anytime when we have a spontaneous reaction that is radioactive, as in for a radioactive substance that emits the particles spontaneously, spontaneously means at will, just emit the radiation without any external influence. That is what is called natural radioactivity. In the periodic table that we have studied, there are some series that are naturally radioactive. Don't forget, we discussed that radioactive elements are always heavy, like atomic number 90, atomic number 70, like that. So in this series, we have what is called uranium series, the actinium series, and the thorium series in the periodic table. Those series and the elements that follow, series, the element, the actinium, thorium, uranium, and the elements that follow them, all of them are radioactive. And not ordinarily radioactive, they are naturally radioactive. They have they emit particles at will, with free will. There's no any external influence, like uranium 236. Uranium 236, by just seeing it in the earth crust, it is radioactive. That is why going close to it is dangerous. Polonium 239, it is naturally radioactive. It doesn't need any external influence to emit particles that it wants to emit. So when it emits the particles, it later forms a stable isotope of lead. All these things that we talk about. That is why lead is also a very poisonous element. So in the other vein, when we have radioactivity that is initiated by bombardment with particles, it is called artificial radioactivity, like that name, artificial. It is not natural, it is artificial. So we have all those elements that ordinarily they are not radioactive, but we can make them radioactive by bombarding them with neutrons. We can also bombard them with protons, but since neutron is neutral, it has no charge, it is more convenient to bombard those elements with neutrons. If it were to be with proton, there is going to be a force of repulsion between the proton we are bombarding and the protons in the nucleon of that element. So another amount of energy will be generated. We will counter the energy that we are using for that reaction. That is a waste of energy. So since 1940, a set of new elements with atomic numbers over 92 have been artificially made. Those elements are called transuranium because uranium is 92. So any element that are obtained as a result of artificial bombardment of uranium or other series, they are called transuranium elements. In corollary to artificial radioactivity, there's another name they call it artificial transmutation. That is when we intentionally turn one element to another by bombardment with either alpha particle or neutron. Alpha particle I mean by a proton. So if you consider this reaction, the first reaction is called Rutherford experiment. So where Rutherford bombarded this nitrogen with alpha particle, this is alpha particle helium. So when it did what it did, so we have another element, oxygen, that is formed, and hydrogen. The same thing, this is Chadwick. When Chadwick discovered neutrons, we said the other time, like lecture 2 or lecture 3, he bombarded proton with beryllium, so he was able to get carbon 12 isotope. So these are called artificial transmutation, when we convert one element into another intentionally by bombardment with other particles. It is a type of artificial radioactivity because ordinarily it cannot occur like this. That is why we call it artificial transmutation. So another important application of radioactivity is in nuclear fission. That is where a bulky nucleus of an atom is split into two or more simpler nuclei. When we have a big nucleus, we now intentionally split them into small nucleus, small, maybe 2 or 3 small nuclei with emission of energy. This process is always exothermic. Then the amount of energy that are released then are used, and the energy that are used, we can produce nuclear power or nuclear weapons. This is actually important, as in some countries, like in China, like in Iran, this reaction is very, very useful to them. So when we have what is called a chain reaction, when we bombard when we have heavy nucleus that split into smaller ones, those smaller ones will split again into another smaller ones compared to them. So far they are not stable, they will continue to split. So when they split, they generate energy. The amount of energy that are generated are being used to provide energy. If it is electrical energy, you can produce electrical energy with it. Like they have their own light in Iran, courtesy of this reaction that is called fission chain reaction. They use uranium-235 and plutonium-239. If there is controlled fission reaction, it generates energy, nuclear energy, which can be electrical, as the case may be. Then if there is not control, that is atomic bomb. That is just the difference between the abused use of nuclear fission and properly harnessing the usefulness of nuclear reaction. If it is controlled, we have a useful product. If it is not controlled, we have destruction. It's atomic bomb. So the other one is the nuclear fusion. Fusion means joining together, combination. When we have two small nuclei, they now combine to form heavy nucleus. It is called nuclear fusion. This one is it needs energy to combine. So when we have small nuclei, we use energy to combine them together. Then that combination, because there is going to be reaction as an energy release as a result of reaction between the combined protons in the nucleus. So because when they are closer to each other, as we discussed in the last lecture, there is going to be electromagnetic energy which will be higher than strong nuclear force. So when we have electromagnetic force, electrostatic force, then there is going to be a very large amount of energy released as a result of this process. It has various applications, like we have it in nuclear fission. It can be by blessing, but can be a cause depending on the way it is used. So we have been talking about radiation energy. How do we quantify it? How do we measure them? So there are many instruments that are used to measure radioactivity, which depends on the properties of the machine and what we need those properties to do. Properties can be accuracy in detection, can be cost, can be robustness, can be size, it can be energy needed to operate. So there are many properties that are considered, but that is not our job here. Our job is just to know. In fact, the principle of operation is less of our concern. Physicists should be able to do justice to that. So these three are the mostly used instruments to measure radioactivity: Geiger counter, scintillation counter, and window GM detector. So before we go, let us look at some of what we have talked about right from the last time, the last lecture to this lecture. There are two forces between the particles of the nucleus: the strong nuclear force and electromagnetic force. We have talked about that. In atoms with large nuclei, the electromagnetic force becomes greater than nuclear force. Then there's going to be energy released. Radioactive decay occurs when an unstable atomic nucleus loses energy by emitting particles or electromagnetic waves, as the case may be. Then the particles and energy release are called radiation. Then such atoms are called radioactive substance. Radioactive isotopes are called radioisotopes. The discoverance of radioactivity was first done by Marie Curie, then husband P. There are three types of radiation from radioactive decay, which could be alpha, beta, and gamma. During alpha decay, alpha particle is released, consists of 2 protons and 2 neutrons bound together with low penetration power because they are heavy. For beta decay, a beta particle is released where a neutron is converted to a proton and an electron are a neutrino. Don't forget that we said neutrino is a very small packet of energy. A beta particle is the electron that is released. That is electron that is released apart from the proton and the neutrino. It has greater penetration power than alpha radiation. Aluminium can stop it. An alpha particle or ordinary paper can stop it. Gamma decay, however, electromagnetic energy is released in gamma decay. Gamma radiation has the highest penetration power of the three. No charge, no mass. Elements do not change. The remaining sources of radiation, some are natural, others are man-made. The half-life of an element is the time it takes for half of the atoms of a radioactive isotope to decay into other atoms. Radiation can be damaging. You can have positive use of it. However, radiation, the positive aspect can be used in treasure in biochemistry, where the negative can be damage to cell, can be cancer, can be genetic abnormality. Then we have to define nuclear fission and nuclear fusion. This is going to be the end of nuclear chemistry. Now before we go, let us solve some examples and take some homework to demonstrate what we have learned. Cancerous growth are cured by exposure to what? From our discussion, to treat cancer, we said the cells are exposed to gamma ray, because gamma ray travels very fast. It has no charge number, so there's not going to be any adverse effects to the exposed area, but it is deleterious to the cancerous cells. That is why it is being used. So gamma rays are used in medical treatment of diseases. The radioisotope used in industrial radiography for the rapid checking of faults in weights and casting. We talked about cobalt-60 the other time, and I could remember cobalt-60 and carbon-14 that we checked. We said they are used in dating archaeological studies and finding fault in casting. Cobalt-60 is a very important radioisotope in radiography. The knowledge of half-life can be used to do dash. Is it to create an element? No. To detect an element? No. To split an element? To irradiate an element? To split an element, because it is the time it takes the element to split into two. And this is a reaction that needs balance. How to balance it? We know this is a beta particle, and beta particle here, up here we have 0, and down here we have -1. It means this element, it has increased the atomic number by 1 from 6, then the mass number remains unchanged. So the release of beta particle here has caused carbon to become nitrogen, because it's only nitrogen that is having 7 atomic number, then 14 atomic mass. So treatment of cancer, detection of leakages in water mains, detection of ages of ancient tools, preparation of drugs. Which combination of the above refers to the use of radioactive isotope? In what we have discussed, it is only in preparation of drugs that we don't have radioactive isotopes don't find application. Option C is the answer. 1, 2, and 3. So these are homework. So after the questions are very simple, they are simpler compared to what we have discussed now. So after solving it, let us check our answer to see if they are correct. This is radium, and to form radon alpha particle, we know alpha particle is 4 and 2. So if you add 4 to x, it must become 2 to 6. So what is the value of x? We see it from the answer. Compare it. This exam question of 2004, question 40, type R. This is sodium 23. Bombardment of sodium with neutron. We just discussed it now, to form another atom of sodium. This is what? Bombardment with either neutron or proton is called dash, and it is artificial transmutation. That's we have said. Option C is the answer. So when we have deuterium and tritium, they now form proton and neutron, then together with energy. Then this reaction illustrates what? What does it illustrate? When we have two lighter nuclei combining together to form one heavy one, with release of energy. That is called nuclear fusion. I think it is the other way around. Now when this one split into this, it will have been nuclear fission, but this one is nuclear fusion. Option C, use of energy. So thank you very much for listening, and don't forget to share and like our videos.